Good afternoon, everyone. My name is Nasser Akhtar, and I'm a speaker in this presentation. Today we'll be discussing what quantum computing is. So I'll be going over the roadmap of this presentation, a brief description, and two of the basic principles. So the roadmap of this presentation includes a few of the basic principles, its history, some real-world applications, a few of the challenges that exist today, what the future of quantum computing will hold, and finally a summary of our presentation. So quantum computing is a new way of processing information that can solve problems much faster than regular computers. It was first developed in the 1980s, but its history dates back to the early 1900s, and it has the potential to revolutionize fields like cybersecurity by enabling the optimization of complex systems. And it does face several challenges, such as high costs, but scientists are actively working on solutions. So what are the basic principles, and how can quantum computers leverage superposition, entanglement, and parallelism to revolutionize computation? A few of the basic principles are processing, quantum stability, parallel processing, and quantum connectivity. So quantum computers process information very differently than classical computers. Quantum computers use qubits, which unlike regular bits have more than two states. Quantum parallelism also allows a single quantum operation to process multiple states at once. Quantum logic gates work mainly on probabilities rather than deterministic outcomes. And when paired with advanced algorithms, quantum computers can process information way faster than regular computers. Since qubits are extremely sensitive, quantum computers need to be kept in highly controlled environments, where specialized equipment regulates all environmental factors. Qubits require extremely cold temperatures, vacuum-sealed chambers, and specialized electromagnetic equipment for precise control. Because qubits are non-deterministic, error correction algorithms such as Shor's, Steen's, and the surface algorithm are used to get usable results. Qubits are also manipulated by lasers, microwaves, and other precise equipment that is accurately controlled by regular computers programmed for these specific purposes. Now I'd like to hand it over to Noah, who will discuss the next two basic principles.
Thank you, Nasser. As he said, my name is Noah, and I will be presenting the rest of the principles, as well as the history of quantum computing. Now, unlike classical computers, which work linearly, quantum computers compute data in parallel. They do this through superposition, which allows qubits to be in multiple states at the same time, both 0 and 1. This allows them to calculate many possibilities simultaneously, unlike classical computers, which have to increase the number of cores or clock speed. A quantum computer can have a number of states equal to 2 to the power of the number of qubits inside the computer. For example, Google's Willow quantum computer can be in 40 nonillion states at the same time, using its 105 qubits. Quantum computers can utilize entanglement for enhanced information transfer and communication. Entanglement allows two qubits to be interlinked, which lets them share the same values, no matter how far apart they are. This allows for the instant transfer of information across any distance and helps distribute secure quantum networks. Entanglement is utilized by quantum algorithms to drastically speed up computation. Next, what is the history of quantum computing, and what are its key milestones? The early origins of quantum computing began in the early 1900s. During this time, scientists such as Albert Einstein pioneered quantum mechanics. The first instance of this happened in 1900 when Max Planck proposed the quantum hypothesis. Afterwards, scientists would continue to expand quantum mechanics through the 1900s to today. Quantum computing was born in the early 1980s, where scientists such as Richard Feynman pioneered quantum computing and explored how quantum mechanics could impact computation. The first instance of this happened in 1980 when scientists gathered to discuss quantum mechanics and computing for the first time. Afterwards, in the 1980s and 1990s, scientists would design early quantum gates to allow for the utilization of qubits. Quantum algorithms, which allow for the utilization of quantum computers, were invented in the late 1990s. Peter Shor and Love Grover made the first quantum algorithms in 1994 and 1996, respectively. These algorithms, known as Shor's and Grover's algorithms, showcased the potential of quantum computing and sparked further investment and research in it. Then, in the 2000s, businesses began to race against each other to build bigger and better quantum computers. In 2011, the first quantum computer, known as the D-Wave 1, was released by the Canadian company D-Wave Systems. Then, in 2019, Google managed to outperform a classical computer using a quantum computer for the very first time. Now, I'd like to hand it over to Gian, who is going to discuss the applications of quantum computing.
Thank you, Noah. Hello, everyone. I am a speaker, and I will be going over the applications of quantum computing and the question, how will it transform the way we use computers today? Some of the applications are quantum cryptography, quantum internet, quantum machine learning, and data management. Quantum cryptography utilizes the principles of quantum mechanics to secure data exchange, leveraging quantum entanglement to create encryption keys that are impossible to decode. Some of the key takeaways are quantum cryptography relies on quantum mechanic principles, it uses quantum entanglement for secure exchange, it uses encryption keys that are virtually impossible to intercept, and information exchange is highly secure and protected. Quantum Internet can create a secure communication network leveraging quantum entanglement and key distribution. The key takeaways are that quantum computing can employ quantum entanglement for communication. It establishes highly secure communication networks. Quantum key distribution ensures that any interception attempts are detectable, and it has the potential to revolutionize cybersecurity and data privacy. Quantum machine learning can accelerate machine learning algorithms, leading to more advanced AI systems. Quantum computing can enhance machine learning algorithms. It offers immense processing power for AI development. Advanced AI systems can tackle complex problems, and AI systems provide more accurate and efficient results. Data management for quantum computing can manage and process massive amounts of data, providing faster and more accurate results. And it can harness immense processing power, and it efficiently handles and analyzes vast amounts of data. Quantum algorithms can accelerate data processing, and data analysis yields highly accurate results. And I'll be handing it off to Suhab, who will go over the challenges, the future of quantum computing, and the summary of the presentation.
Thank you, Gian. As you heard, my name is Suhaib, and I'm the last speaker today, discussing the challenges and the future of quantum computing. So, what are the challenges? How are quantum computers being held back from changing the world today? First, we have hardware limitations. Quantum computers need extremely cold temperatures to work properly. Even small changes in the environment can mess up calculations. Second, we have error rates and stability. Qubits are really sensitive and can easily lose their state, causing errors. Fixing these errors is hard and takes a lot of extra resources. Third, we have scalability and practical use. Cost, or making bigger, stable quantum computers is really tough. At the moment, they aren't much better than classical computers for most tasks. Fourth, we have cost and accessibility. Quantum computers are expensive to build and maintain. Only big companies and governments can afford to develop them. Now, what is the future? How close are we to a future powered by quantum computing? First, we have error correction. Scientists are working on better error correction codes to make quantum computers stable for longer periods. Scalability. Advances in superconducting qubits, trapped ions, and photonics could help scale quantum computers. Third, we have cloud access. Bigger companies are making quantum computing available via the cloud. Some revolutionary applications: quantum computing could transform medicine, AI, encryption, and material science. Summary. Quantum computing is a new type of computing that can revolutionize the way certain problems are solved. The history of quantum computing dates all the way back to the early 1900s. Quantum computing can revolutionize several industries, including AI and cryptography. Quantum computing faces tough challenges, but scientists are actively working on overcoming them. These are our references. Finally, thank you for listening to our presentation on quantum computing. We hope you gained a better understanding of its basic principles, history, applications, challenges, and future. As this technology continues to evolve, we encourage you to keep up with the latest advancements because quantum computing might just change the world sooner than we think.